Hi, my name is Felix Moore. I'm working at Universidad de la Sabana in Colombia, and I'm presenting self-optimizing random forests today. So, random forests are ensembles of decision trees which typically create axis-aligned splits to separate data from different classes. But you can also create oblique splits by rotating the data in each inner node prior to creating the actual split. And depending on the rotation you choose, you get better or worse performance. So the rotation itself can be subject to optimization. And one possible goal then is to say, okay, let's build the random forest for the rotation type that obtains best performance, and find this as fast as possible. Find this random forest type as fast as possible. So the idea of this paper is to incrementally train forests of different tree types, and for each of them during training we project the performance curve to get an estimate of how the best performance possible with this tree type can become. And as soon as this estimate gets stable, we stop. And once we have done this for all the for the tree types or rotation types, we pick the most promising one and train it until convergence. This way we get a speed up of 50% on average compared to training all the forests until the end. And also as a side effect, we get rid of the hyperparameter that controls the number of estimators, which is also very important. So here we study forests of three different types. First the standard random forest, and then forests in which in each node we create a or conduct a principal component analysis or a linear discriminant analysis prior to creating the actual split. One could in theory also mix trees of different rotation types, but we don't do this in this paper, basically to avoid confounding factors, but that's certainly something interesting to look at in future work. So the idea of a SORF is simple. For each forest type we do the following steps in each iteration. So in each iteration of training a forest of a specific type, we add and train a new tree, and then we record the out-of-bag estimate of the forest. Then this gives an empirical curve of performance observations, and this curve can be extrapolated using some curve model. Here we use a Morgan-Mercer-Florian model on a smoothened curve, and we stop as soon as the limits projected by this curve model on the last k iterations have shown very little variance. So this means that this curve model somehow has now converged, and we then pick once we did this for every forest type, we pick the one with the best projection and add trees until it actually converges, and not only we have converged projection. So the first thing we want to make sure is that the SORFs don't deteriorate in performance, and here we see the accuracy of the self-optimizing random forest on this axis, and on this axis the performance we get with each of the three random forest types in isolation. And what we can see is that virtually in all of the 96 data sets, so 1 point for every dataset and every random forest type, we get results with the SORF that are at least as good. So we are basically not deteriorating. This is something that you would also expect, even though it's not obvious, since we are doing projections with a performance curve, and that could introduce wrong decisions. Apparently this is not the case here, so that's a good news. The question is how much time can be saved, and here we focus on this box plot, which shows for each tree type what's the time that the SORF spends on training trees of this type compared to the time the random forest of that type needs to be trained on 100 trees. And this is here aggregated for the 96 datasets and for each tree type. And the last one here, that's the most important one, shows what's the overall training time of the SORF divided by the time we would need to train the three other random forest types, each one with 100 trees. And we can see here this dotted line is the mean. So on average we have a reduction of 50% in runtime, and sometimes it's even much more. up to here almost 90% runtime reduction. So in a nutshell, self-optimizing random forests get optimal performance across the different tree types in only half of the time, which is a quite amazing result. So the main limitation of this work is that the forests are currently homogeneous, so only one tree type is allowed for the whole forest. The most obvious change here to be considered next is to mix the different tree types and to look what are the effects of having trees of different types and whether we can get the same performance results, because if this is the case we could even speed up this whole training process for source more, because we need even less trees in total. If you're interested in the code, check out the GitHub repository and I would be happy to discuss this in the poster session with you. Thank you.